Good day everyone, my name is Ray Banting Flores and welcome back to my YouTube channel. Last week I have already uploaded my video presenting or solving for the related rates problem involving ladder, balloon, and a cylinder. And I also uploaded my video solving for the tangent line and a normal line using the first derivative of the function serves as the slope of the tangent. So for today, we will be presenting or discussing the indeterminate forms in the type of 0 over 0 and infinity over infinity. So this video serves as a brief introduction as well as a sort of review before we proceed into the other topic and that I'll be dealing or uploading here in my YouTube channel. So the objective of this video is that at the end of the lesson, the learner should be able to evaluate indeterminate forms type 0 over 0 and infinity over infinity. So in this video, I'll be using two ways, which is the one, I guess it is the most traditional, which is the direct substituting, but not directly substituting because you just need a little bit of effort before you can substitute the value of the given. And also the second one would be the L'Hopital's rule. So first example here is we have the limits of x squared minus 4 all over x minus 2 as x approaches to 2. So if we just directly plug in the value of 2 to the variable of x, we have the square root of 2, the square root of 2 is minus 4 is equal to 0, and on the other hand, in the denominator, we have 2 minus 2, which is equal to 0. So therefore, the given here is in the form of the indeterminate form of the type 0 over 0. That's why, as what I have said, direct substitution, but it requires you to exert a little bit of effort. So in this case, we just first factor out the numerator. So we have x minus 2, x plus 2, all over x minus 2 as x approaches to 2. And by that, we have the same in the numerator and the denominator. So we just simply omit or cancel those to have the remaining limit of x plus 2 as x approaches to 2. And in this case, we are able now to substitute or plug in the value of x, which is 2, to the variable x. We have 2 plus 2, which is equal to 4, as the value or as the limit of x squared minus 4 all over x minus 2 as x approaches to 2. Number 2 is we have the limit of sine x all over x as x approaches to 0. So if we just plug in the x or the value of x, which is 0, to the variable of x, without prior knowledge, you will have the solution of 0 over 0, which is indeterminate form in the type of 0 over 0. But in this case, if you have the prior knowledge of common limits, um, for this given here, you will have the value of 1 as the solution for these limits or the limits of this given here, which is sine x over x as x approaches to 0. I guess it is in the number 3 of the common limits list. So indeterminate forms, or solving for the indeterminate, it can base the idea that the limit cannot be determined without additional work. So you must just exert a little bit of effort. So next is we will go to the next way how to solve for the or deal with the indeterminate forms, which is the Petals rule, which is in the form of the limit of f prime of x all over g prime of x as x approaches to c, which is equal to its limit. So L'Hopital's rule is applied taking the derivative of the numerator and the derivative of the denominator separately, not this derivative of the quotient. So if you are planning to use L'Hopital's rule in dealing indeterminate forms, you should always remember that you must derive the function, both the numerator and denominator, separately, not in the derivative of the quotients. The quotient. So we have here the first example applying the L'Hopital's rule. So the limit of ln x or natural log x all over x as x approaches to positive infinity, we have the limits of ln x or natural log x as x approaches to positive infinity, which is equal to positive infinity. And the limit of x as x approaches to positive infinity, it will be equal also to positive infinity. So therefore, this given here is in the indeterminate form type infinity over infinity. Since we are using a L'Hopital's rule, remember that we must derive the numerator and denominator first separately. So we came up with the derivative of ln x, we have 1 over x. Derivative of x is 1. So we have the limit of 1 over x all over 1 as x approaches to positive infinity. Simplify, so we came up with the limit of 1 over x as approaches to positive infinity is equal to 0. Therefore, x grows faster than the natural log of x or ln x. Next is we have the limit of x all over a raised to x as x approaches to positive infinity. So we have the limit of x as x approaches to positive infinities is equal to positive infinity, the limit of e raised to x as x approaches to positive infinity, which is equal also to positive infinity. So the same that the given is in indeterminate form type infinity over infinity. Applying L'Hopital's rule, deriving the numerator and the denominator separately, so we came up with the limit of 1 all over e raised to x as x approaches to positive infinity, which is equal to 0 if we plug in the value of x to the variable x, which is a raised to x grows faster than the natural log x. Another example, we have the limit of 3x squared plus 2x minus 1 all over x squared plus x as x approaches to negative 1. The same process, we have the limit of 3x squared plus 2x minus 1 as x approaches to 1, just plug the value of negative 1 to the variable x, so we came up with 0. And the other hand, for the denominator side, we have x squared plus x as x approaches to negative 1, plug in the negative 1 to the variable x, we came up with 0, which is the given understood that is in indeterminate form type 0 over 0. Therefore, we must apply L'Hopital's rule and derive the numerator and denominator separately. So we came up with the limits of 6x plus 2 all over 2x plus 1 as x approaches to negative 1. And by that, we will be plugging in the value of negative 1 to the variable x. We have 6 multiplied by negative 1 plus 2 all over 2 multiplied by negative 1 plus 1 is equal to negative 4 all over negative 1 is equal to 4, positive 4, as the limits of 3x squared plus 2x minus 1 all over x squared plus x as x approaches to negative 1. The last example for today's video is the limits of tangent x minus sine x all over x squared tangent x as x approaches to 0. So without further explanation, we can understand that, or able to understand that this given here is in the form of an indeterminate form type 0 over 0. And by that, we need to apply the first example we have presented, the number 1 first example, which is we reform or apply a little bit of effort, and then we have the limit of 1 minus cosine x all over x squared as x approaches to 0. So do not worry, because this is the process how we got that 1 minus cosine x all over x squared as x approaches to 0. So we have tangent x minus sine x all over x squared tangent x. We all know that tangent x is equal to sine x over cosine x. So just simply replace tangent x. So we have sine x all over cosine x minus sine x all over x squared sine x minus cosine all over cosine x. So simplify, so we came up with sine x minus sine x cosine x all over cosine x all over x squared sine x all over cosine x. So just simplify again. So we came up with sine x quantity of 1 minus cosine x all over x squared sine x. Just omit or cancel the sine x, so we have the remaining value of limit of 1 minus cosine x all over x squared as x approaches to 0. And by that, we're now able to find or apply the L'Hopital's rule. So we have limits of 1 cosine x all over x squared as x approaches to 0. So applying L'Hopital's rule, so we have the limits of sine x over 2x as x approaches to 0, which is equal to 1 half. 1 half because, as you observe here, 1 half multiplied by sine x over x it will be equal to sine x all over 2x. And we all know that in the second example I have given, sine x all over sine x is in the common limits, and it is understood that it would be equal to 1. So therefore, 1 half multiplied by 1 is equal to 1 half. L'Hopital's rule can also be used for one-sided limits. And that would be all for my video. For today's video, I hope you have learned, and please do subscribe, click the notification bell, and leave a comment. And that would be all. Thank you and bye bye.